All right. So you remember from before, hopefully, that I told you any system, any mechanical system. I said any vibrating system, but that's a general rule for any mechanical system that you're dealing with. It has three elements, right? An element that stores kinetic energy, and we said, well, a good example of it is a mass or inertia if you're dealing with a rotating system. An element that stores, well, the previous one was kinetic energy. If I said something else, I was wrong. Kinetic energy, which the example of it is mass or inertia. An element that stores potential energy, which good example of it is a spring. And then in the last class, we saw actually stiffness. We talked about the stiffness, and we saw how can we even convert typical systems made of solid materials into a set of springs. Right? So that type, right, a spring or a stiffness can store potential energy. And the last element is something that dissipates the energy, something that because of that system loses energy, right, to its environment, and that's damping. Now, previously we talked about viscous damping. You know, that's the only type of damping we talked about and you're familiar with, at least up to now in this course. Now, what I'm going to do today is that I want to talk about a different type, right? A type that is more familiar to you, and there is a reason we did not start with this, because you will see this is less straightforward and the way we deal with it. So viscous damping is the most common one that we use when we deal with systems, because it's very well behaved. You know, when we are writing equation of motion and we want to solve it, when we use viscous damping, it's much easier to solve the equation and, you know, find the system response. Now, you'll see for this type of damping, which is pretty much caused by friction. That's why it's called Coulomb damping or dry damping or dry friction. Any of these names are used usually, typically, if you look at different textbooks. This damping, well, again, it's something that you already know, right? A good example of it when you're rubbing your hands together, right, is friction. I'm pretty sure all of you are very familiar with the concept of friction at this point, after being in the engineering, in mechanical engineering for more than 3 years. Now, this is the way, and you know, friction takes energy out of system, right? When we have friction in a system, obviously the system tends to stop after some time. When you push a box, or when you have even a vibrating spring and mass, but the mass is on a very rough surface, after some point, that's going to stop. So let me put it on there. Coulomb friction. Coulomb damping, I'm going to put it this way. Coulomb damping, or in parentheses, dry damping or dry friction. The reason we call it dry friction, well, because it happens when bodies are sliding on dry surfaces. Right. So if I want to put a few words here, again, I'm not going to introduce the concept of friction. You already know what friction is. You've seen it multiple times. You just want to look at it as a concept, as something that we can take into account as a damping mechanism, since it takes the energy out of the system. So just one line, I can just say it happens, or it occurs, put it this way, when bodies slide on, let's say, dry surfaces. Mainly, obviously friction exists even if the surfaces are not fully dry. You still have some friction depending on the coefficient for that direction. The coefficient for that friction changes, right? The mu value changes, but you still have it. So to study that, right, we are going to take a look at the simplest possible system we can have. Right? A spring and mass. an element that stores potential energy, an element that stores kinetic energy, plus now we're going to add the Coulomb damping to the system. That being said, pretty much what I'm trying to say is that, let's put it this way, that we have a spring mass system that is oscillating on a rough surface. Right? It's a dry surface that we have friction. Up to now, we have been always ignoring friction. I was telling you there is no friction between the surface and the object, or I was putting some small wheels under the mass to show that, you know, there is no friction, that much friction. So in this case, let me just put a simple system here. Let's keep the color the same. This is the mass. This is the spring. It's K, this is M. And now it's oscillating or it's moving on a relatively rough surface. Now we have friction. Now, in order to get the equation of motion for this system right, what they do is that they divide this motion into two cases. The equation of motion you get, let's put it this way, changes. So it's not like before that you get one equation of motion and you're good to go and you solve that. The equation of motion changes depending on the sign of the velocity of this mass, or x dot. So I'm going to put it under two cases. Right? Let's say case one and case two. Case one is going to be the case where the velocity is positive. So if I want to draw the system again, let's say we are somewhere here. And if this was the equilibrium point for this system, let's say, I'm sorry. So this is the spring, and it's a little stretched now. Thank you. I think it's a little bit of allergy in the morning. So this, and this would be the equilibrium point, as straight as I could make it. This is K stiffness, this is mass, and this is the surface we have. So in this case, velocity is positive. It's going in this direction. This is x dot. And the second case, there are more cases obviously, but other cases, if you actually go into details, the equation of motion would be very similar. If you want to divide it into smaller cases or more detailed cases, I would say. The second case they consider is, consider this as equilibrium point. Still the spring is stretched. But now we are in a situation that velocity is negative. We're coming in this direction. X dot is negative. It's the direction of the velocity. This is the surface. This is K. So I do the whole finding the equation of motion simultaneously for both of them, or relatively at least try to make it simultaneously. If you look at the left one, case one, this case, let me draw some line here. So it's less. And if I draw this free body diagram for this box, whatever that mass is, I have my normal coming from the surface. I have mg. Kx is to the left. It's trying to pull the system back to its equilibrium. And since we're moving in that direction, friction would be in this way. I'll call it mu n directly instead of fk. For the one on the right, let's draw the free body diagram here. This is the mass. I have the normal here, N. I have the mass mg. The spring is still taking it this direction, right? Because it's trying to take it back to equilibrium point. Now motion is to the left, so friction is against the motion. Friction would be this. Now if you write the equations, right, take the right as positive for all of these. The first one you'll get minus, let me start from here, minus kx minus mu n is equal to mx double dot. Move things around, this becomes mx double dot plus kx is equal to minus mu, and n is equal to mg, so I'll just put it here, mu mg. This is the first equation. The one on the right, I'll get minus kx plus mu n is equal to mx double dot. I'm taking the positive for both, same direction. So the equation of motion for this becomes mx double dot plus kx is equal to mu n. Or let me just replace n with mg. All right, this is normal to the surface. Find the summation of forces in y direction. N becomes becomes mg. So I'll just plug it here, mu mg. Second case. So I get two different equations. I can mix, put them together, right? If I call this one, equation two. Equation 1 and 2, actually, I can put them together, right? With a little bit of math. It's still two. It's still a set of two equations, but you can kind of mix them together by saying mx double dot plus mu mg sine, which is a sine function, x dot, plus kx. So it looks more like the equation of motion we had for a system with damping, right? Mx double dot plus cx dot plus kx for viscous damper. Now this is more close to what we had for a viscous damper. Now if I draw this sine function, hopefully you have seen sine function. I'm just going to draw it here. Pretty much is positive when we are on the positive side, and it's negative when we're on the negative side. So if this is sine x dot, and this is x dot, because we said it depends on the velocity, the equation we get at the beginning. No? So this would be an equation or a function in this form. You can think about it like this. It's pure mathematical. This would be minus 1, right? Then this would be plus 1. I'm sorry, guys. I do have an allergies, apparently. Okay, so it's positive and negative. What happens? Well, obviously when x dot, let me just add it here, make sure we all know what we're talking about. X dot is greater than 0. X dot is the x-axis. Sine x dot becomes 1. And when x dot is smaller than 0, sine x dot becomes a minus 1. This is just a kind of review that if you forgot what sine function was. I don't deal with sine functions, so I can totally imagine you also probably forgot what it was. So it's good to just have it right there. So all I did was just use sine function to write these equations in just one, in the form of one equation of motion. Now the problem with this equation is that it's not a very well behaved equation as what we had before. When we were dealing with a system with a viscous damper, things were nice. Mx double dot plus Cx dot plus Kx, it was an equation of motion, second order differential equation, homogeneous, we could easily solve and, you know, get the system response. Now in this case, this is a nonlinear differential equation. If you look at this, because of this sine function, it makes the whole equation or differential equation nonlinear. So it's not, we cannot find an analytical solution for this. It's not as straightforward as before. We can solve it numerically. You probably, in numerical methods, your course, you may or may not have dealt with nonlinear differential equations, and you saw how can you use different numerical approaches to actually solve them numerically. Right? But this is vibration. We are not going to do that, obviously. But hopefully you know how to do it if you want to. So this is a nonlinear differential equation. However, there is a way that we can solve this. Instead of looking at this final equation, which is nonlinear differential equation, we're going to look back at equation number 1 and 2, right, for different two possible situations, depending on what the sign of the velocity of the system is. What we can do is that any of those equations, if you look at equation 1 or equation 2, it's actually a second order differential equation. In this case, non-homogeneous. We have some constant on the right side, like for equation 1 is minus mu mg, for equation 2 is mu mg. We can actually solve them separately. Each of them we can solve. Right? When we get together, when we put them together, we cannot solve. So let's do that. That's what they do. They solve these equations one by one for any for different phases of the motion. So the first phase is when the velocity is positive, or actually we're going to start, I guess, from the end, when the velocity is negative. And then when the velocity is positive, and again solve it for the next. So we are going to solve this for different half cycles. So every time we are all the way on the right side, imagine, look at case 2, right? If this is the mass, the velocity is negative, comes all the way, passes the equilibrium point, gets to the all the way to the right side, or goes from the right side, goes all the way to the left side, stops there. This is half a cycle. What was a cycle? A cycle was when the mass starts from one side, goes to the other side, and comes back or gets close, as close as possible to where it was. That's one cycle. Now, going from this side all the way to this side is half a cycle. Velocity is negative. And the second half, we are going to go from all the way on the left to all the way to the right. This is the second half cycle. And that's where the velocity is positive. So we can actually solve the equation of motion for each half cycle, because the next half cycle equation of motion changes, we have to solve a new equation. Let's take a look at how does that work. So let me see if I have a better wording here. Okay, we can solve the equations of motions for this system, in parentheses, analytically, obviously. Numerically, we could solve it even from the beginning, for the whole, the general equation we could solve analytically. So we can solve the equation of motions for this system if we break the x, or let's put it this way, time. Well, let me see if I have yeah, I don't have a better one. Time axis into segments. That is good. Separated by x dot is equal to 0. trying to say the same thing I said. Go from one side, velocity is negative, all the way to this side. It stops there. It changes the direction. Velocity becomes positive. So for each of these segments, we have an equation of motion that is easy to solve, relatively easy to solve. A second order differential equation is non-homogeneous. We know how to solve. So let's start with all the way. Let me make sure that I told you everything I wanted to say. Yes, I did. Okay. So let's start from this case number 2. Right. The reason we start from there because the equation of motion is like the right side is positive, and we're more comfortable with starting from positive side. The displacement, or x, is positive in this case. We're all the way to the right. So starting from case 2, where the mass is all the way to the right and about to move towards left. And go all the way on this side, going in this direction. Now in that case, well, when you're all the way here, the mass stops for a second, right? Before the velocity was right this way, positive. Now velocity wants to become negative, so we stop there for a second. We get to the end of this half cycle, and we start the motion from that sudden or very short moment that the mass is stopped. That you can probably, hopefully, get the initial condition, right? We have a differential equation, second order, we need initial conditions to solve it. So when we're all the way to the right, the moment that we are switching the direction, the velocity is 0. The velocity at that time, I'm going to take that time as t equals 0. Right? That's where we start our analysis. So the velocity is 0. Meter per second, millimeter per second, whatever the unit is. Now, when we're all the way to the right, we are at some distance, like x naught, whatever the distance is. That I'm going to consider that as the initial position for the system. Call it x naught. Now, I have this along with the equation of motion, which we already found when we're going in that direction. We said it's mx double dot plus kx is equal to mu n. That was the equation of motion. Now, as before, we've dealt with this before. Hopefully now you know that whenever we're dealing with an equation of motion, I just give you a suggested solution. We don't argue about that because pretty much is math. And as I said before, technically we never solve a differential equation. What you did in the course differential equation you had was, whenever you had a differential equation, you just needed to know what type of differential equation is that, and if it goes to the specific category, you were given a set of possible or suggested solutions for different types of differential equations, and you were just using that specific general form of the solution, and you were trying to find the constants using some initial conditions or boundary conditions. Same thing here. This is a second order differential equation, and it's non-homogeneous. We have mu n on that side. Actually, mu mg. Let me just follow what I did there. I plugged in n as mg. So what you do is, maybe I'll go with n, so it's easier to write because I have to write this multiple times. But n is equal to mg. Keep that in mind. I think in the equation I just plug it in. I just want to make sure that it doesn't cause confusion. So here, what I'm trying to say is n is equal to mg. Right? For this one also, n is equal to mg. In y direction, if you write the equation, the equilibrium, you'll get that. All right, so this is second order differential equation with non-homogeneous and it's not homogeneous. We have something on the right side. So the general form of the solution, I'm going to suggest, right, the suggested solution would be xt is equal to a1 cosine omega 1t plus a2 cosine omega and t. Let me see if I did the same thing there. The second one is sine plus a2 sine omega and t. Hopefully I did plus mu n over k. You can actually get this from what you know from differential equation. Mu n is the non-homogeneous part is just a constant. We had a method to find what is this to find this mu n over k. Now, since we have the general form, let's find the coefficients. You know, the idea is that I am given initial conditions, and this is the suggested solution with this differential equation. Now let's find the coefficients that I don't know, which are a1 and a2. So if plug in these, so let's go with, well, I have to find the derivative. Let's go with x naught t equals to x naught. For x at t equals to 0 is equal to x naught. So plug in, this becomes, well, x naught becomes cosine 0 is 1, so this becomes a1. Sine 0 is 0 plus, and that is just a constant. So from here I can find a1. a1 would be x naught minus mu n over k. So the first constant in this suggested solution I found is a1. For the second one, x dot at t equals to 0 is 0. If I take derivative, the first term, a1 cosine omega n t becomes a1 minus a1 omega n sine omega n t, and t equals to 0, so it becomes 0. The second term, let me put 0 is equal to. The second term, a2 sine omega n t, if I take derivative, it becomes a2 omega n cosine omega n t. Cosine omega n t at t equals to 0 is 1, so I'll get a2 omega n, and omega n over k, third term, if I take derivative to find x dot, so I can plug in t equals to 0, mn mu n over k is 0. It's just a constant. I'm taking derivative with respect to time, becomes 0. So all I get is a2 omega n is equal to 0. Now omega n cannot be 0 all the time. This system has some natural frequency, right? If omega n is equal to 0, it's a trivial solution, because what does that even mean? There is no system. Why are we even doing this, right? So a2 becomes 0. If I plug this in into suggested solution, right, now I know a1 is this, a2 is 0, so xt, I'll call it x1, let's say do that, becomes x naught minus mu n over k cosine omega n t plus, well, a2 is 0, so there is no second term, plus mu n over k. So this is the system response. That's not the color I wanted to use. This is the system response for the first half cycle. Mass is all the way to the right. Oscillate, it starts moving from that point, comes all the way to the left. Ends where the velocity becomes 0. Goes from here to here. So let me write it this way. System response for the first half cycle of the motion. What does that mean if you consider t as a time period for the motion? Means this is where time is greater than or equal to 0 and smaller than or maybe equal to t over 2. Half cycle. T is the time period, meaning that it shows one cycle. So for half a cycle, t changes for this equation from 0 to t over 2. Half a time period. All right. So, as I said, we have to continue this. We keep going like this. So first half cycle, now we look at the second half cycle. At this point, the mass is all the way to the left, and it's about to move to the right. So that's where the velocity is positive. So this was for case 2. Now we're going to do it for case 1. Right, go back here. Case 2 was when you were going this way, velocity was negative, and case 1 is when the velocity is positive, so we go all the way to the right. That's where we are. So I'm going to use the equation of motion number 1, that mu mg or mu n on the right side is negative. So I'm going to continue this. Now I'm looking at the second half. As I said, I have to solve these one by one, each half separately. So for the second half, of the cycle, or for the second half cycle, second half cycle, right, we look at case 1. The equation of motion was well, let's start with boundary conditions or initial conditions, sorry, to follow the same formatting we did for this case. So now this is the equation of motion. We are all the way to the left. Motion started. First initial condition wasn't that hard. Here equals to 0. I said, well, velocity is 0. We started the motion. And we are in some initial position. Right? I stretched this mass. I pulled it all the way to one direction and I let it go. And let's say that position was x naught. Now, how about now that we are in the middle of the motion, we come all the way to the left, what are the mass stops for a fraction of a second and the direction of the motion changes. How about now? What is the initial condition for this moment? How do we find that? This is not the beginning of the motion. We don't know how far, at least by first look, here we knew we stretched this spring and took the mass all the way at some point x naught. What is the initial condition at this moment now when I want to start looking at the second half cycle? I need to know the initial conditions, right? I know the equation of motion for that half cycle. I found it before. But in order to find the differential equation, I need to know the initial conditions. How do I find those initial conditions? Does anyone have any idea or suggestion?
You can use this equation of motion to find the, so it would be the equation of motion for the second part of the motion.
Yes, I believe that's, you said what I wanted to hear. I have the equation of motion system response, right? This x1t describes the motion at any given moment while I'm in this phase. So when the second half cycle starts, it starts from where the first half cycle ends. Where am I when the second half cycle ends? Obviously, if I put a t equals to t over 2 or half the time period in x1t, that's where I am. This xt describes the motion and where the system is at any given time during the first half cycle. So the last moment I'm in the first half cycle would be the first moment for the second half cycle, which becomes the initial condition for the second half cycle. So all I need to do is that I use the system response, x1t, and plug in t equals to half time period. So to find the initial condition, I'll call it x2. Let's say x2 at t equals to t over, well, x2 at t equals to 0 for this specific part of the motion is x1 at t equals to t over 2, wherever the previous motion ends. Now t over 2, well, you know t equals to 2 pi over omega n. So t over 2 would be pi over omega n. Right? Hopefully you followed with it. Time period, half a time period, you know, from previous equations, we know t equals 2 pi over omega n, so t over 2 would be pi over omega n. So if you put time as pi over omega n in this equation, it becomes cosine omega n times pi over omega n, right? So omega n will be cancelled by omega n, right? This becomes this. This becomes cosine omega n times pi over omega n t. Right? Get rid of this. Well, there is no t. I replace t with pi over omega n. So it becomes cosine pi. What is cosine pi? Cosine pi?
-1.
-1. Okay. For a second, I was having a heart attack. Becomes -1. So this becomes minus times x naught minus omega n, mu n over k. Right? The second part, mu n over k is just, you know, going to be there. So this becomes minus x naught minus mu n over k plus mu n over k. This minus, you apply this minus to this, whatever we have in parentheses, this becomes, let me see if I did that. This becomes, this becomes x naught minus 2 mu n over k. Apply the minus, sum these two up, 2 mu n over k, and then took the minus out. So this becomes the initial position for the mass in the second half cycle. How about the initial velocity? How much is the initial velocity for the second half cycle? It's 0, right? We don't really go through the whole process of taking derivative and plugging in pi over omega n again. We know that the mass stops at the last place because the velocity is going to change its direction. So it stops and it starts moving in the opposite direction. So the velocity is 0. We already know that. Now this, along with the equation of motion that we had for that half cycle, go back, remember equation of motion 1 for what? Mx double dot plus kx is equal to minus mu mg. I'll go with mu n in this case. So equation of motion was mx double dot plus kx is equal to minus mu n. Now again, suggested solution for this would be very similar to what we had. I'll call this x2t, so it's not confused with the previous response, system response. I'll call, these are different constants. So I'll call this A3 cosine omega n t plus A4 sine omega n t. This time this becomes minus mu n over k, the constant. So we have the suggested solution. We have the initial conditions. All we need to do is to plug in. So x2t at t equals to 0, we know becomes minus x naught minus 2 mu n over k. We found it from before. So this means at t equals to 0, we'll get minus x naught. Let's keep it the way it was. Becomes minus, there is a reason I write it this way, minus 2 mu n over k becomes, well, cosine 0 becomes A3, right? Minus mu n over k. Sine is 0, so we get rid of that.
So I can find A3 here. Goes there. Hopefully I do the math right. It's positive, positive. So this becomes minus x naught minus 3 mu n over k. Did I do it right? Let me double check. Hopefully I did right. This goes there, positive. No, I did not do it right. Positive, positive. So I guess if I'm not wrong, cosine 0, this is minus, this becomes minus x naught plus 3 mu n over k. And if I factor out the negative, okay, that works. Minus x naught 3 mu n over k. Correct me if I'm wrong. I think I did correctly. So double check. Now x2 dot at t equals to 0 is equal to 0. Take derivative, the same process as before. This becomes 0 is equal to a4 omega n, and that'll give you a4 is equal to 0. There. So the system response now for this part, or second half of the cycle, becomes x naught minus 3 mu n over k cosine omega nt. I'm just plugging in a3 minus mu n over k. Did I do it right? Hopefully I did. So this becomes a system response. Now this is the system response for the second half of the cycle. Second half cycle. This case, the general t would be from t over 2 to t. So it goes all the way from one side to another side. The first half, the second half starts from this end. Velocity is positive, goes all the way to the other end. Now we can continue this, obviously, right? And the third half, fourth half cycle, that's how they solve this, right, analytically. You just keep going. Now, if you do the whole process, obviously we're not going to continue this going on and on. Right? You get the idea how do they solve this. What we care about is, as before, if we plot this, right? Let's plot this, see what we have. Let me make sure that I told you everything. Oh, I think. If I plot these half cycle system responses, right, one by one, and put them all together in a graph. Let me draw it here, the schematic form of that. Here is what you get. You get something along this line. I'm trying to draw it as good as I can. Let me do it this way. So this is x naught. This is where you started the motion. The axes are, this is x, it's a function of t, and this is time. Go back there. Now, the time period for this system, right, it's the same time period as the spring mass system. Remember, the time period for a viscous system and the viscous damping was different, right? We had 2 pi over omega d being the damp natural frequency. But in this case, we have a spring mass system. The damping that we took into account was just friction. It does not affect the time period. So the time period still would be 2 pi over omega n. Right? That's the one difference between this type of damping and viscous damping. The time period stays The second difference would be if you connect these peaks, which I didn't do a great job plotting them, but if you connect them, or connect these, you remember when we were talking about viscous damping, this line was an exponential decay. Here is not the case. This is just a linear relationship. Connecting those peaks together, you just get a linear relationship. So it's pretty much a line. Now that line's slope would be this. Let me try harder. If you look at this line's slope, that would be minus 2 mu n omega n over, I believe, pi k. Pi k. Omega n natural frequency, n being the normal force, you can replace it with mg, or depending on what kind of system you have. That's the slope that this line makes with the horizontal line. Going forward, let's take a look at what is the value here, this magnitude. Right? When we start from x naught here, go all the way to this end, this is half a cycle. Keep in mind, one cycle, one half a cycle, second half a cycle. Right? We go from one side, x naught is where we are, we let it go, it goes all the way to the other end, and that's the other end. This is the other end, this point. So this is half a cycle, and this x is where we are, or what is the position of the mass at the end of the first half cycle. We found that. We found it as the initial condition here. There you go. This is the value of that. So if I go all the way there, I just put it here. This magnitude is minus x naught minus 2 mu n over k. The same process, if you go to continue this, first half cycle, second half cycle, you use the equation of motion you found for the system response for the second half cycle and find where does it stop at the end of that cycle. Right? This is the second half cycle. Going from here all the way to the other point at the top. This would be the position at the second half cycle. Or if you do the math, you'll get the value. Let me see if I can use a different color. And be less messy. That would be difficult. If this is there, this would be, right, that magnitude there would be x naught minus 4 mu n over k. Now, you will see there is a relationship. I'll introduce that relationship. That's what we care by the end of the day. One last thing on this plot that, keep in mind, this is the time period is t in this system, that you remember. One last thing is where does the system stop? You see, I plotted this way. It doesn't reach 0. So there's a difference between, there is a gap. If you think about that spring the mass, right? We had N, we had mg, where spring was pulling it back with, let's say I'm on that side, and the friction is stopping the motion, mu n. Now, when it stops when the kx force, the first force from the spring, is not strong enough anymore to overcome the friction. So the moment it stops would be the moment that kx is equal to mu n. Or around that moment, kx becomes a tiny amount less than mu n, it can't move that. The friction is going to hold the mass wherever it is. So this system is different because at the end, the mass does not come back to its equilibrium point. It stops away at some distance away. What is that distance? Is mu n over k. This is this distance. You see the gap between the position of the mass and the horizontal axis, x equals to 0. So this is mu n over k. So a few things I want you to remember about this. First is the equation of motion is nonlinear. Right? The equation of motion is, let's put it this way, equation for a system with Coulomb damping is nonlinear. We saw that. As opposed to what we had for viscous damping, which was pretty linear. Second thing is that the natural, unlike, let's put it this way, unlike the case for viscous damping, natural frequency of the system doesn't change. Doesn't change. Let's try to put it here. All right, I said t equals to 2 pi over n, time period is the same, natural frequency is the same. So it's not like viscous damping. Third one is that, as I said, the system comes to stop somewhere that is not the equilibrium point, and where the friction force is less than or more than this force of the spring. I'll leave it there. I don't put it as a extra, I would say, step. Now, one thing that we like to look at is the number of half cycles before this motion stops. So if you give it some initial velocity, initial displacement, and let it go, what happens? And keep in mind, we solved this equation of motion system for a special case, the case in which initial velocity was 0. We did not talk about the case that we give some initial velocity to the system. Right? That would be a different story. That's not what we got. Everything I explained here, everything I said is for a spring mass system sliding on a surface with some dry friction, given the fact that initial velocity is just an initial displacement. Initial displacement is given, and initial velocity is 0. So one thing we care about, or we want to know, is that when we let this mass go at some given initial position, initial displacement, how many half cycles this has to go through before it stops, before we get to a point that the spring force cannot overcome friction. That you can find, actually. So number of half cycles, let's say before the motion stops, when we go about it, we say, well, xt or x naught minus, I'll put it this way. I cannot write for some reason. X naught minus 2 n, let's say the number of half cycles. I'll introduce n as a number of half cycles. So n, lowercase n, mu n over k, right, should be smaller than or equal to mu n over k. Keep in mind, mu n over k is where it stops, right? So as long as this displacement, we found this x here. Take a look at the plot. This is where we said it's going to stop. So wherever this is, right, this set of reduction or reduction in the motion we keep having for every half cycle, at some point we say, well, this is valid, right? It's smaller than or equal to the where it stops at the end. So the rest is just to move things around. If you do that, I'll save you from the headache. So I'll just do the last thing. I'll take n out of this. So n would be greater than or equal to. If you do this, you'll get this relationship. X naught minus mu n over k divided by 2 mu n over k. So now this n is the number of, right? This is the number of half cycles before the system stops. So you can calculate that, knowing everything we know about this system. Last thing about spring mass system on a dry friction is that, well, we saw that the amplitude reduces if you plot this system response. I said if you connect the tip of these tip points, right, peak values, you'll get a linear relationship. So the amplitude reduces linearly, right? It's not like what we had, that the amplitude was reducing exponentially for viscous damping. So let me just put it here. The amplitude reduces linearly. And let me see if I have something better here. If you want to write it this way, you can write it this way. Whereas it reduces exponentially for a system with viscous damping. System with viscous damping. And this reduction actually you can calculate. So the reduction for two successive peaks, I would say, yeah, peaks is good. If I call this xm, would be xm minus 1, the peak, the maximum value of the peak I had from before, minus 4 mu n over k. This is the relationship that you kind of saw it, right? If you look at here, this is the magnitude first half cycle, x naught minus 2 mu n over k. And then after a cycle, you got this one, x naught minus 4 mu n over k. So how many peaks you go, that is going to define, you know, how much the magnitude is going to be reduced. But this is the relationship between two successive peaks for one cycle. You can rewrite it this way as delta x is equal to 4 mu n over k if you want. The amount reduction in the amplitude from this peak to the peak after is 4 mu n over k. Either of these two, depending on how you want to think about it. So we started, we went through a lot. We started the spring mass with the spring mass system. We said, well, now a spring mass system, it's moving on a dry friction, a dry surface. You know, these are what we could do. We could solve the equation of motion for every half cycle. We found how does the system behave. The time period doesn't change. The amplitude reduces linearly, and we can find that reduction for successive peaks. And we could even find the number of half cycles before the system stops, because we know where does it stop. What I wrote there, mu n over k. These are pretty much all you need to know about this system. I'll just quickly take a look at this straightforward example, hopefully. We have, let me write this example for me. We have an experiment is run. So let's write this problem statement. An experiment is run to determine the kinetic coefficient of friction between a block and a surface. So this is more like a system identification process. And a surface. Now the block is attached. I can actually ignore this part of the problem statement. We have our block here. I can draw it here. Mass M. And spring is connected. This is K. This is the surface. We know X naught is 150 millimeters. It's stretched to some amount from equilibrium point. And we are given, let me write this. It's observed that the period of the motion is 0.5 seconds. It continues. And the amplitude decreases by 10 millimeters on successive half cycles. So we are asked to find the coefficient of friction and number of cycles. Pay attention, it's asking for number of cycles, not half cycles. Number of cycles of motion before the block stops. All right. Here are the information I have. Initial position is given, time period is given, the amplitude reduction is given. I have to find what is pretty much what I gave you. What is the time period? We have to find first. Well, we have the time period. We have to find how much the is the coefficient of friction and the number of cycles of motion before the block stops. So I'm looking for mu and n. The introduced number of, well, not exactly n. N would be the half cycle. I'm looking for 2n. Pay attention that I introduced n here, right here, the third point number 3, as the number of half cycles. So when we say number of cycles, would be 2n. All right, try to go faster, but feel free to stop me if one part doesn't make sense following what we just said. So I have time period. Well, let's just start from where I know what I know, or let's do it this way. Let's say I want to find, well, I know the amount the amplitude is decreased, so I know delta x. And I said delta x is 4 mu n over k. And this is just a typical spring mass system. So if this is n, this is mg, my n is equal to mg. So I'll just write 4 mu mg over k, delta x. The problem is I don't have the value of mass, and I don't have the value of stiffness. Do you see what the problem is? I have delta x. Delta x 10 millimeters. 10 millimeters would be, this is equal to 4 mu mg over k. I know g, obviously. I'm trying to find mu, which is the coefficient of friction, but I don't know m and k. These are unknowns, which is not good. I only have one equation, 2 unknowns. So what do I do here now? M is unknown and k is unknown. So now it's a problem. But I do know the relationship between m and k. If you go back, it tells me what is the period of the motion. It's 0.5. So the period, right, I can find natural frequency from there, 2 pi over t. And I can just say 2 pi over 0.5. This becomes, well, 4 pi. I'll just leave it like that, rad per second. What is omega n? Well, omega n is the square root of k over m. So now that I know it's kind of a relationship between k and m, all I need to do is have to write the equation I had for delta x as a function of natural frequency. Now, if I take that from here, let's now do it this way. I can take mu out. Right? Let me start from the beginning. Delta x is equal to 4 mu mg over k. So delta x is equal to, I'll write it 4 mu g. I take m down. It's going to be k over m. K over m is omega n squared. Right. Let me do it correctly. I write it as times m over k. This is just one. Now I can rewrite this 4 mu g omega n squared. This being omega n. This is omega n squared. So from there, I can actually take mu out. Now I have pretty much everything I need. Mu would be delta x, hopefully I do it correctly, delta x over, if I did it, oh, I see what mistake I made. Nobody's stopping me. I guess everyone wants to just finish the class. This is not omega n squared. What was omega n? Square root of k over m. This is m over k. So this is 1 over omega n squared. Because we know omega n, or omega n squared, is k over m. Now it makes sense. 1 over omega n squared. Now from there I can find mu. Mu is equal to delta x omega n squared over 4g. I have delta x 0.01 omega n square omega n I found, plug it in, 4g. If you do the math, you'll get 0.04. That would be your coefficient of friction. The same story about the other equation for n, right? Half cycle. I said n is greater than or equal to, I said x naught minus mu n, I'll put n as mg, mu mg over k divided by 2 mu mg over k. I do the same thing. I say, well, x naught is equal to, well, x naught minus, I'll write it as mu g over omega n squared. Right? What I did is that I took m over k. M over k, I said, is 1 over omega n squared. So I can write it that way. Divided by 2 mu g, again, omega n squared. M over k is 1 over omega n squared. Now I have everything I need. X naught was, initial position was 0.15, 150 millimeters, minus plug in these values, like mu g over omega n squared. You found mu, you know omega n now, 2 mu g over omega n squared. We know all of these. This becomes n is greater than or equal to 29.67. Now the last thing, this is the number of half cycles. So number of cycles, how do we deal with this? What we do is that we always round this up. Right? We round this up, we say n is greater than or equal to 30. And from there, divide it by 2. Because you can't divide 29 something by 2 to get the number of cycles. So this means that you have 15 cycles. If you have 30, half a cycle, you have 15 cycles. Just one thing, I realized that the reason I wrote here, maybe you shouldn't have wrote 2n here, create confusion. And number of cycles. All right, this takes me to the end of the class. 1 minute extra, I kept you there. Sorry about that. But if